Hello, good morning, everyone. Today, inshallah, we will continue on our seek for optimality in various cases. Of course, as usual, you will find all of our resources either on Moodle and the recorded lectures. You will find them on our YouTube channel as usual. Okay, today we will continue on the equality constraint with an objective function. This is really a very important topic and it has a massive application almost in every aspect of field. So as I told you, today we will talk about we will dedicate this lecture to the case of having one constraint or constraint optimization of a function mainly in two variables. So today we will try to reach the case of having just only two variables and one equality constraint. We will study the suitable methods and techniques to handle this matter. As I told you, it's really very important, especially in our major. Okay, we will start by the famous Lagrange multiplier method. This is really a very important method and it is really very successful, either in the functions or in the cases of just only having one variable or in multiple variables, as we will see down the road with the rest of our lecture. As I spoke with you, or as I told you, the Lagrange multiplier method is a technique used in constraint optimization. That's to find the maximum or the extremum of a function, which is the objective function, subject to a constraint, to an equality constraint. Okay, let's start. We will study the case of having a function in two variables and just only one constraint. Let me get my laser point. So this is the function required to be optimized, either to get its maximum or to get its minimum value. So in the situation of having, for example, increasing or maximizing the profit of a certain company or a certain institute or something, we will be maximizing. On the other hand, if we are talking about costs and stuff like that, we will need to minimize cost, to minimize our expenditures, getting the best of the objective function or the purpose of the objective function, whatever it is, subject to one constraint, one inequality constraint. So we will get the optimality of this function, but satisfying with the satisfaction of this equality constraint. Assuming that we can get the main idea, assuming that we can get y as a function in the in x from this constraint and resubstituting in the main function. So this is mainly what's going to happen. Of course, in some situations, it's really very difficult to just isolate y out of the constraint function. And we may need the derivative of this function. So we will be in need to get back all our information from the implicit definition of the implicit function theory. Thus, we can sub by the constraint in the objective function and having a function connecting everything together. So if we have f small over x and y, that's our optimality function, and we have g of xy, which is our constraint that must be satisfied, we will seek to have y as a function of x and resub in the optimality function. So we will have a new optimal function, which is h of x. Consists of x and h small of x, which is the implicit definition from the constraint. In such a way, this function will connect both of them, the objective function and the constraint, together in one function, which is h capital of x. And this is the strategy that we will depend on. So once we do this, we will get back to the unconstrained cases that we already studied before. So the strategy, find the potential extremum point, and this is really very simple. All I have to do, as we used to do this previously, getting the first order derivative of h of x and then put it equal to 0. And this is how we are going to get our critical points or our extreme point. Step number 2, trying to classify these points. Either it is a maximum point or a minimum point. So that's the study of the sign in the second derivative at those points specifically. So f h double dash, which is the second derivative of h over x, the function, once more connecting the whole problem, both the objective and the constraint function, both together, and connecting them together. Okay, so after getting the critical points, we will make this substitution. If the value is greater than 0, as we know, we will have a local minimum, exactly like what happened before and what we trained on. And if the double derivative or the second derivative is less than 0, then we will have a local maximum. Let's start by getting h of x. After getting h of x, we will find the potential extreme point by setting the first derivative of h dash of x equal to 0. And this is really very simple step. Once you remember all what we have learned previously from our study. Okay, so mainly I want you to remember that y of x is an implicit function. So differentiating it, we will need to use the implicit function theory. So please try to review this part before we continue. It's really very simple. So once more, trying to differentiate h of x, it's going to be differentiation of this function with respect to its variables, which are partial f partial x plus partial f partial y times dy by dx. And this part here is the part that we will use the implicit function theory in order to have it. And this is really very simple. If you remember from the implicit function theory, all we have to do is to get dy by dx for the function partial g partial h, which is the constraint, minus, of course, with negative sign, divided by partial g partial y. Of course, satisfying that the first partial derivative of the constraint with respect to y is not equal to 0. Once we get dy by dx, we will make this substitution in h dash of x. And this is what we are going to have. I want you just to focus on this equation directly, which is h dash of x. This is the first term. It's exactly as it is. We just replaced dy by dx by the value that we have here from the implicit function. So this is the end of our substitution. But remark, if we, since partial f partial y of xy times partial g partial x divided by partial g partial y, we can replace these two guys. And then we will have this form, which is the first derivative for f with respect to x minus the constraint with respect to x times the derivative of f as whole with respect to y divided by the differentiation or the derivative or the partial derivative of g with respect to y. Setting h dash equal to 0, we will have this value. This is, I want you to take care of this value or to remark this ratio, which is the derivative of f with respect to y divided by the derivative of the constraint function with respect to y. Stop. Once more, remember from the beginning that we are optimizing a problem, that having an f, which is the optimality function, the function that we need to optimize, and we have g, which is the constraint. Okay, very good. This guy, I will define it by lambda, which, as we will see just in seconds, that's this value, which is lambda. That's what we call a Lagrangian. So the function will be partial f partial y for f of x minus lambda partial g partial y equal to 0, where lambda is defined by the partial derivatives of f with respect to y and for g with respect to y also. So that's the lambda stand for the Lagrangian multiplier, as we will see. Now, the candidate to extremum points are found through the system of equations that we already have. So the first step, as we will see, is to get our function, which is the Lagrangian function, as we will see, getting the partial derivatives with respect to x, with respect to y, and with respect to lambda, as we will see, which is going to be the constraint or the condition. This system, once you put it equal to 0, we will be able to determine the extremum point. So I've thought it's a very good idea to summarize these steps for you. So starting by getting the first derivative of x, then get the system of equation represented by the Lagrangian multiplier, solve the system, and study the case by case separately, as we will see. But instead of doing all of this work, we can do something very, very nice. So once more, instead of solving the system to get our critical points, we remark that we can instead find the Lagrangian multiplier function, which will make things more smooth and easily to handle. But this system of equation corresponds to the first order conditions of the function. So mainly, this is the Lagrangian function. As you can see, I can put this function really, very easy, which consists of having the function required to be optimized, plus, or to get the optimal point for it, or to search for extremum for this function, plus some lambda, which is the Lagrangian multiplier, times the condition. But for the constraint or the condition, you must put it equal to 0 and use this. I myself usually use g of xy minus b equal to 0, as you will see, and this sign will be negative. So it works fine both ways, either writing g of xy minus b, and of course the sign outside this bracket is going to be negative, or using the Lagrangian function definition that's given in front of you. Okay, let's go through this step by step. So once more, getting h dash equal to 0, solving the first order condition together, and then the Lagrangian from the Lagrangian function. Second, study the case and the sign of the second derivative of those points, which is going to be an easy task. Once we go to the second derivative, once more, we will need to find the derivative of h double dash of x, of h dash of x. And of course, it's going to be a little bit complicated since we are using the implicit function theory. This is why I told you we will have to review it. We will need to study the sign of the critical points obtained from step 1 by getting second derivative with respect to x, as I told you. But remember, once more, this is a composite function. So differentiating this guy will end up with the Hessian matrix times some factor. This remark, I wrote it for you on the side after derivative, and for some simplification, we will find that this is the Hessian matrix in some negative constraint, or on some negative constant, I'm sorry. So that's the Lagrangian function that we spoke about earlier in the previous slide. This is the function, and that's the condition once we put it equal to 0. And then we will go through the Hessian matrix. The Hessian matrix represented the second derivative, but involving also derivative with respect to lambda. So we will differentiate the Lagrangian function with respect to lambda twice. Then we will get the mixed derivatives, as you can see, and so and also for the column it will be the same. And then we will differentiate the Lagrangian 2 times with respect to x, and the mixed derivative with respect to x and y with the similar definition. Of course, once you do so, we will have this relation in front of you. That's the partial derivative of the constraint in all cases with respect to x. That's the partial derivative of the constraint with respect to y. The second derivative with respect to lambda always goes to 0, because if you remark here, if we differentiate this guy with respect to lambda, we will have b minus g of xy, which is the constraint, and it doesn't depend on lambda. So once you try to find the second derivative of this part, it will be equal to 0 in all cases. Now we will come to this shape, which is exactly what we want to have, which is defined by the border Hessian matrix. which we will depend on its sign in determining the type of our extreme. Okay. Second, if we get the border Hessian matrix, which is going to be very simple, as you will see from the coming example that will clarify everything for you. You will find it really very easy to handle. But just wait for the coming example, and it will put all of these steps all together working perfect. Okay, this is the sign of the determinant of the border Hessian matrix. If it is less than 0, remark that the Hessian matrix will be greater than 0, and so we will have our classification. So if the determinant of the border Hessian matrix is negative, so if this guy is negative, then the determinant of the Hessian matrix is positive. That's the H star of X is a local minimum. So I want you to remark that for the border Hessian matrix, it's apart from the Hessian matrix. This part, if its determinant, I'm talking about this part only, is less than 0, then we will have a local minimum. And if this guy is greater than 0, then we will have a local maximum. Okay. We are in need for an example to summarize all of this. Once more, remember that we have the optimality function plus the constraint required to be satisfied in order to make in order to get our extremum point of the objective function with the satisfaction of this equation or that constraint. So all we have to do directly after getting this relation, which is the Lagrangian function, okay, we will get the first order derivative and trying to solve the results of this first order equation, getting the critical points, keeping them, then we will get the Hessian matrix, as you will see. Depending on its sign, we will be able to determine for this critical points if it is a maximum, extremum point, maximum, or minimum, as we will see. So let's study the case of this example, which we handled previously in the previous session. So let's consider the optimization function. It's x plus y, and it's subject to one constraint, which is x squared plus y squared equal P4. This is really very simple. All I have to do now is to form the Lagrangian function. And this is very simple. All I have to do is to get f of x, y, which is the optimality function first, plus some lambda, which is the Lagrangian multiplier, time the constraint. So let's construct this step by step. So here's the Lagrangian function. Remark, that's the objective function. If you can see, that's exactly the objective function in place. Then plus lambda 4 minus x squared plus y squared. So that's the constraint in putting it equal to 0 and inserting it into the Lagrangian function. This step is a major step, and it's really very important, very simple. All I have to do, once more, to take the objective function or the function, we need to search for its optimality, putting first plus the lambda plus the constraint that we have. We will have first put it equal to 0, then substitute in the Lagrangian function, as you can see. The second step is to find the first order conditions, which is going to happen from differentiating this guy or these functions with respect to its variables, which is really very simple. So all I have to do is to differentiate lambda with respect to x, and then putting this first partial derivative equal to 0. So let's do it. Differentiating the Lagrangian function with respect to x is really very simple. This is going to be 1. That's going to be 0. And don't forget, this guy will be negative 2x times lambda. So our result will be 1. That's the x derivative. It's going to be 1. For the second part, differentiating, it's going to be negative 2 lambda x. Here we go. That's lambda negative 2x. I will put it equal to 0. That's the first equation. In a similar manner, differentiating the Lagrangian function with respect to y. So differentiating the function with respect to h is going to be 1. differentiating the second part, which is going to be lambda times negative 2y, as we can see, and putting it equal to 0. Finally, we will have our constraint, which is simply x squared plus y squared equal to 4, which is really very simple. So once more, what we have done is forming the Lagrangian function, getting the first partial derivative with respect to its variables, which are x, first derivative with respect to x, first derivative with respect to y, then with the first derivative with respect to lambda, which is going to develop the constraint. So I can use the constraint directly. Unfortunately, these equations, in some cases, they are nonlinear. So you will have to think of them and to take most or all the possible cases in this solution. So the second step, we can get 1 on the opposite side. So we will have 1 equal to x lambda and also 1 equal to 2y lambda from these two equations, which are zeros. Okay, so for lambda equal 1 over 2x, and from here, from the second equation, we also can get lambda equal to 1 over 2y. So that's lambda equal 1 over 2x, 1 over 2y. Putting them together will lead to the fact that x equal to y. So once x equal to y, that's the result that we got from solving these two equations together. We will make a substitution by this result into our constraint and see if it is satisfied, if it is logic, if there is a contradiction, as we will see in the coming problems. But for the time being, all we had to do is just to make this substitution. So here is the constraint. We will replace y by x. So we will have 2x squared equal to 4, which will give x squared equal to 2. Taking the square root for both sides, we will have x equal to positive or negative root over 2. Now I know the value of x, so simply I can get the value of lambda, which is going to be a 1 over positive or negative 2 root 2. If you have the value of lambda, then I can get directly the value of y. Or since x and y equal to each other, then y will equal to positive or negative root 2, and that's lambda. We usually like to write them in this manner. This is the lambda value, that's the x values, and that's the y values. Okay, so now these are the stationary points or the points that are candidates to be an extremum point, either maximization or minimization based on the nature of your analysis or what are you going to do or interested in. Now, getting to the sign of the border Hessian matrix, which is very, very simple. All I have to do once more, that's the initial values or the stationary point that we already had from the previous slide. Okay, I have the first order derivatives, partial the Lagrangian with respect to h, which was 1 plus lambda negative 2x, 1 minus 2 lambda y, as you can see, and here is the constraint. Now I will go to the Hessian matrix. Remember, that's differentiating G with respect to lambda once more. We don't have lambdas here, so it's going to equal to 0. Then differentiating this guy with respect to x, which is going to develop to x. Differentiating this guy, which is the constraint, the G, with respect to y is going to be 2y. We can just get the transpose of these two parts and insert it here in the first column. Now I will get the second order derivative of the Lagrangian function with respect to x. That's the first partial derivative. So I will differentiate this guy once more with respect to x. So differentiating this guy with respect to x once more will develop negative 2 lambda, as you can see. Okay, differentiating this guy with respect to y, we don't have y's here, so the result will be 0. Once more, I will go for the second derivative, as you can see, with respect to y. So I will take the first derivative and start differentiating with respect to y, which will develop a negative of 2 lambda, as you can see. And those are the mixed derivatives that we have. If you look, this is the border Hessian matrix, which is -2 lambda, 0, 0, -2 lambda. Now, I will try to get the determinant of this guy, which is going to be 4 times lambda square. 4 times lambda square. If we substitute by the value of lambda at the critical point, we will have a value greater than 0. And if it is greater than 0 for the border Hessian matrix, then the sign of the whole Hessian matrix is going to be a negative, which stands for a local maximum. So for the point where x is positive root 2 and positive root 2, we will have a local maximum point. In a similar manner, if we use the second point, which is negative root 2, negative root 2, and try to insert it in the definition that we have, we will have a negative 2 root 2, which is a local minimum for this 2 points, which were the stationary points of the function. So let's put this all together once more. First of all, get the Lagrangian matrix, which is the objective function plus some lambda times the constraint. Second step, after forming the Lagrangian function, I will differentiate it with respect to x, then with respect to y, then with respect to lambda, which is the constraint by itself. From the first two derivatives, I will put them equal to 0. Then solving these two equations together, or this system of equations, will enable us to get the stationary points that we want to discuss their nature. The second step, after determining these values, which in this step also, before going to the next step, in the first step, getting this stationary points, after getting the derivative equal to 0, I will use these relations and substitute once more in the constraint. This is how we get the results of x and y. Using these equations with the help of the constraint, we will be able to identify the value of lambda, the value of x, and the value of y as you saw or as we see. Then I will get the border Hessian matrix, which can be got really very easy by differentiating the first order derivative once more, and we will get the border Hessian matrix, this guy. Once you have the border Hessian matrix, you can get its value, its determinant value, and then use the stationary point, and then based on the sign of the border Hessian matrix, you can identify if it was a local maximum or a local minimum, as we saw in this example. What we are going to do now is to go to m variables in m constraints case, which is a generalization of what we had studied previously. So let's do it. The theorem states that if we have f such that its domain belongs to Rn, is a subset from Rn, and it goes into R, be a differentiable function, and considering the following optimization problem, m less than n, okay, here we go. That's the optimization function, f of x, and these, the bunch of the equality constraints that maybe we will subject to. I want you to remember that m is the number of the equality constraints that we need to satisfy. So we can summarize the steps to be: first, form the Lagrangian function. That's step number 1. Step number 2, get the stationary point by differentiating the system and putting it equal to 0. Number 2, get the border Hessian matrix exactly as we did in the previous slide. It's exactly the same. After getting this determinant of the Hessian matrix, we will be able to identify the nature of our stationary point. So let's go to step 1. First of all, that's the form of the generalized Lagrangian matrix, which is, Lagrangian function. Here's the function required to be optimized. Those are the conditions we need to satisfy during the optimization of f of x, which is called by the Lagrangian function, and where lambda, of course, the Lagrange multipliers. X star will be the stationary point of this Lagrangian function. Step number 2, consider the border Hessian matrix, which is a square matrix m by n. Very, very simple. And this is the formulation and of the Hessian matrix, and that's the border Hessian matrix that we spoke about earlier. Okay, very good. We studied the sequence of leading principal minors, but of order 2m plus 1. I want you to remember here that m is the number of the constraints. If you have one constraint, so we will start by getting the order of order 3, the leading principal minors of order 3. Okay, if I have two constraints, so I will get with 2 times 2, which is 4 plus 1. So I will start with getting the order of 5 and so on. If all have the same sign, I'm talking about the leading principal minors of -1 to the power of m, then f of x is a minimization point. If they are alternating in sign, I'm talking about the leading principal minors, that's the sign is equal to -1 to the power of m plus 1, then fx star is the maximum, and that's a generalization of the condition. Once more, for 1000 times, remember that m is the number of constraints inserted in your problem. Otherwise, it's not possible to conclude what's gonna be. Let's try this method on a problem as we will see, an example which will actually lead the way and make everything make sense coming together. So let's consider that we are searching for an optimization for x minus y plus 2z, and which is subject to x squared, y squared, 2z squared equal to 2, which is our constraint. And that's an equation of an ellipsoid, of course. Okay, first step, this is the Lagrangian function, which consists of the f of x, which is the function required to be optimized, plus the Lagrange multipliers times the constraints that we have. Here we go. That's our Lagrangian function. That's the objective function minus the constraint that we handled or inserted in our problem. I want you to remember, if I move x squared, y squared, 2z squared to the right side with a negative sign, so here is going to be, this sign is going to be positive. But if we move 2 beside x squared, y squared, 2z squared, then we will use this guy with a negative sign. Both of them work fine, so I want you to be aware of this step. First order conditions, I will try to differentiate the Lagrangian with respect, remember, with respect to x variables. We have 3 variables here, x, y, and z. So I will get the first order derivative for this function, partial derivatives, of course, with respect to x, with respect to y, with respect to z, and subject to the constraint as we will see. Here we go. Differentiating with respect to x, this is going to be 1, and that's going to be minus lambda times a 2 over x. Differentiating with respect to y will develop negative y, then minus 2y lambda, as you can see. Differentiating with respect to z will develop 2 from this part here, and the negative 4 of z, as you can see. I will put the first 3 equations equal to 0, and here is our constraint that we will use in order to get specifically the values of these functions. Okay, let's try to work out these 3 equations together in order to get our stationary points. And this is really very simple. All I have to do is to just trying to get lambda of x, so it's going to be negative 2 lambda x equal to 1, which leads to 1 equal to x lambda. Then for the second part, we'll develop negative 1 equal to 2y lambda. And for the third part, it's going to be 1 equal to d lambda. If we get lambda from the first 2 guys, it's going to be equal to 1 over 2x. And from the second equation, it's going to be lambda equal to minus 1 over 2y. So if I put both of them equal to each other, I will end up having x equal to negative y. Exactly in a similar manner, putting lambda 1 over 2x equal lambda 1 over 2z, and in this manner, we will get to the relation that x equal to z. As you can see, I've tried to work these equations together, getting the value of lambda from the first equation, from the second equation, equating them together, getting a link between x and the negative y, as you can see, and then getting the first one with the last one, same way like, getting lambdas, putting them equal to each other, and then we will have x equal to z. Now I have relation connecting xy and xz. Of course, I will use them and make a substitution in the constraint function, which is x squared plus y squared plus 2z squared equal to 2. Once we do this substitution, we will have that 4x squared equal 2, that's x squared equal half, and that leads to that x equal to 1 over positive or negative root 2. That's y will be 1 over negative and the positive root 2, and the z will be exactly the same. Here is the values of y. Remember that it has negative sign, so this is why the signs are replaced. And for z, it's going to be the same. So our x, y, and z, we have 2 points, 1 over root 2, negative 1 over root 2, and 1 over root 2 for the z. Or negative 1 over root 2, positive 1 over root 2 for y, and for the z value, it's going to be negative 1 over root 2. Of course, having these values, I can substitute in the first equation and getting the Lagrange multiplier value. Now I have everything, the x, y, and z, and lambda. That's the stationary points are going to be 2 main points as the previous example. It's just accidentally happened. This is the first value of lambda, and that's the x, y, and z, similar manner for the second point. Now I will have to go to find the Hessian matrix, and from it the Hessian border matrix or the border Hessian matrix. Once more, this is just a summary of what we did, the first order derivative, working them all together, getting the results over there, and these are the two stationary points that we already have. Once more, that's the Lagrange multiplier function that we are dealing with. Now, after getting these critical points, we can apply also the Weierstrass or Weierstrass theorem, which states that for an enclosed domain, the sign of the image can define the nature of the point. And based on this, here we go, since the objective function is continuous function, and the visible region is compact, we already have an ellipsoid, as you can see. That's the optimization function, which is represented by x minus v plus 2z. And that's the constraint, which is this ellipsoid. So it's a compact, okay, set. So this truss theorem, we can guarantee that the problem has a maximum and the minimum from the image value. So simply I can use this theory, just substituting by the values of x, y, and z in the objective function. And since at root 2, 1 over root 2, negative 1 over root 2, and 1 over root 2, it's going to be positive. So we will have a maximum value. And at the other point, we will have a minimum value. Also, we can use the Hessian border matrix and get the determinant at the stationary point. And if it was less than 0, then we will have a minimum. Greater than 0, we will have a maximum. So both techniques can work beautifully with no problems whatsoever. Okay. In case we cannot apply the Weierstrass theorem, in this case, we will have to get the border Hessian matrix, as I told you previously. That's the first order derivative. So that's the derivative with respect to lambda. So that's the form of the Hessian matrix in a type of 3 variables. As you can see, that's the first and row and column, which is relative to lambda. This guy is going to be 0 because differentiating once more with respect to lambda will lead to 0. Differentiating the condition with respect to x, with respect to y, with respect to z, and also putting it into the column, then differentiating the second derivatives from the first partial derivatives. This is how we can get our Hessian matrix on this board. So if we want to differentiate the constraint with respect to x, it's going to be a 2 of an x. Here we go. That's the 2x. Differentiating the constraint with respect to y, that's going to be 2y. Differentiating with respect to z, it's going to be 4 of z. These two guys are the transpose in this first column. Okay, for partial 2 lambda, partial 2, the Lagrangian function, or the second derivative for the Lagrangian function with respect to x, it means we will differentiate this guy, which is going to develop negative 2 lambda. Here we go. And also, it will go same way like for the rest of the border Hessian matrix, as you can see. So it's going to be negative 2 lambda, 0, 0, 0, negative 2 lambda, 0, 0, 0, negative 4 lambda. And that's the determinant that I will depend on. Of course, number of constraints is equal to 1. We have just only one constraint in 3 variables. So I will start by getting the sign in order to determine the nature, by getting the sign, okay, of the, remember, leading principal minus from the border Hessian matrix, which will start with 2 times 1, which is going to be 2 plus 1, 3. So I will need the leading border, I'm sorry, the leading principal minor for the Hessian matrix with the third order, which is going to be 8 lambda x square y square by evaluating this guy. Of course, this is going to be a 0 using Sarah's rule to evaluate this determinant. 2x times 0 times y is going to disappear. 2x times y, 2x times 0 times 2y will disappear. Then negative 2y, negative 2 lambda 2y, which is going to develop 8 lambda y square. Then similar manner for the elements under the secondary row, the secondary diagonal, and then multiplying 2x times negative 2 lambda, which will develop with a negative sign, of course, 8 lambda x squared. So it can be summarized to this form. Now I will use the stationary points and substitute in H3 to get its value. In a similar manner, I will need to get the leading principal minors for the whole border Hessian matrix, which is going to come up to negative 64 lambda square. If I used these values, the stationary point values that we already have previously, and they make a substitution in the leading principal diagonal, leading principal minor, I'm sorry, of the border Hessian matrix of third and fourth, we will getting the classification that we will have. So the border is going to be less than 0. That's they are alternate in time, having H3 the same sign of negative m plus 1, which is will develop a maximum. That's a direct substitution in these guys. And also in a similar manner for the second point, we will have a minimum point. Now getting to the last part of our lecture, which is the envelope theory, which will help us so much in solving a lot of problems. The version of the theory when we have an equality constraint. We already have the version of the envelope theory in the previous lecture, and it was really very important summarizing how to put everything all together in order to see the changes that will happen if we have parameters changing in the solution of our problem. So let alpha be a vector of parameters that may change after solving. So we are interested in if one of these parameters change, what's the change that will happen in the optimal value of the objective function. Of course, that's what's all the envelope method all about. So the envelope theorem states that, I want you to remember, that the change in the optimal function due to the change of one of the parameters that's involved in the optimal function, it is measured by the derivative of the Lagrangian function with respect to that parameter at the ultimate point. Okay. Interpreting the Lagrange multiplier, if we change one of the right-hand side of the constraint constants, what's corresponding change in the optimal value of the objective function, that's what the envelope theory will help us with. Let's see an example to put all of this work together beautifully. Okay, we can say that the Lagrange multiplier is the rate at which the optimal function of objective function changes with respect to the changes in the right-hand side, which can be as a shadow price or something. In order to make this more suitable and handleable for you, I will get with you for this example, which will illustrate everything. Here, he is giving you that we were asked to build a rectangular box with a square basis. So I will need to build a rectangular box with a square base and with volume equal to 32 meter cube. This remark here is a constraint by itself. So I want to build up this box, but with under the condition that its volume will be exactly 32 meter cube. The objective to spend as much as possible each meter square of the material needed for the lateral parts, bases and the top. The costs are €1 and €3 and €5 respectively for the bases. For the lateral parts, for the bases and for the top cost, and for the top of this box. So once more, the materials that we are going to use will cost us just only €1 for the lateral parts of this box and €3 for the base of this box and €5 for the top of this box. I want you to formulate the problem explaining what are the decision variables that's going to be the objective function. Solve this problem, getting its maximization or minimization. And then finally, we will study what's going to happen, okay, for the new minimum cost if each meter square of the material for the top of the box costs now €5.1, which means it is increased by a certain value, or there is certain change in the costs of the just only the top of this box. So once more, the problem summary. In such type of problems, I want you to read it more than once. So you read it once to understand the scenario, what's it all about. You read it twice or the second time to try to speculate what are the main decision variables and the constraint, or what's the condition you will have to satisfy. These two things are really very important for you in order to determine a successful treatment for this problem. So we are to build a closed rectangular box with square bases. So the bases should be a square. Number two, volume is 32 meters cube. Number three, the material costs, the lateral side is €1, the base is €3, the top is €5. This is what I'm doing after reading this problem more than once. Number three, the goal is to, what we are searching for is to try to maximize the cost under the constraints that the volume must be satisfied. Then we will need to solve this optimality problem and then find the effect of just increasing the price of one of the parts of this problem. So here's the box that we are talking about. As you can see, that's the base, and these are the lateral sides of the box, and this is the top of this box. Let's formulate the problem. Of course, we are talking about the dimension. So we will talk about the length, width, and the height. That's a general case. But in our case here, we are talking about a square base. So we will have just only the sides of the bases, which is going to be one side, and the height of this part. So X stands for the side length of a square base in meters, and Y the height in meters. And these two guys will control our objective function that we are going to form right now. I want you to remember that the decision variables represent the dimension of the box, as I mentioned to you. And since it has been a square basis, so the two dimensions of the base will be equal to each other. Okay, perfect. The constraint is that the volume, which is x squared y, should be 32. Of course, the volume of a box is equal to the area of its base times the height. So the area is x times x, because it's a square, times the height, which is y. This must be satisfied. Okay, perfect. So the objective function is required to maximize the costs of this building materials. So I will get the area of the basis, which is going to be an x squared, and according to our problem, it will cost €3 for it. So it's a 3 times x squared. And for the top area, it costs 5. So it's a 5x squared. And for the lateral parts, we have 1, 2, 3, and 4. We have 4 lateral parts. Each one of these lateral parts formed from an x, which is the length, and y, which is the height. Here we go. So it's going to be 4xy, as you can see. And the cost is 1. So now we can formulate our objective function to be 4 times 1 euro xy, which is the lateral side, plus 3x squared, the cost of the base, plus 5x squared, the cost of the top of the box, which will come up to an 8x squared plus 4 of an xy. That's our objective function, subject to the constraint, which is x squared y equal to 32. So now from the first part, we already done with it, formulating or modeling the problem scenario and putting it all together to be the total costs, as you can see, and with subject to this constraint. We will continue. That's the Lagrangian, as you can see, function. We put first the objective function, exactly like what we did previously, plus lambda times the constraint that we have, which is 32 minus x squared y squared. Once more, I have moved x squared y to the other side, so the sign will be positive. Please take care of this sign. I've solved problems just moving x squared y inside the 32, and in this case we will use lambda positive, or just moving 32 beside x squared y and the sign will be negative. Okay, perfectly. Now I will forget all about the problem and will focus with the steps in order to get the optimality or the optimal solution from the Lagrangian function. So I will start by differentiating the Lagrangian function with respect to x, with respect to y, and working these two equations together and substitute in the constraint. Please remark, from the first equation, we can, from the second equation, if you remark, we can take x as a common, leaving us with this form, with two alternatives. So taking x as a common, we will have x, open a bracket, 4 minus x lambda, which is going to be like this. Then we'll put x equal to 0, and then 4 minus lambda x equal to 0. So we will have two probable solutions. The first of them is x equal to 0. The second one is 4 minus x lambda equal to 0, which leads to that 4 equal to lambda x as we use. Let's study first the first case, which is x equal to 0. Once x equal to 0 and substituting in the constraint, this is going to be a contradiction, because my understanding that we will need to satisfy that x squared times y should equal to 32. So x will never be equal to 0. We can't put it equal to 0. If you put x equal to 0, then the volume will be 0. So 0 equal 32. It's not going to work. So it contradicts our constraint. It will be refused. So this will leave us with just only that that 4 minus x lambda equal to 0. That's lambda equal 4 over x. If lambda equal to 4 over x, and then we substitute in the first equation, we will have 4, then substituting lambda by 4 over x will make this equation much more easier, as you can see, okay? And it will be on this form, 4 of y plus 16 of x minus 2xy times 4 over x equal to 0. And simply, we will have that y 4 of x equal to x squared y, which is going to be 32, leads to 4x cubed 32, that's x equal to 2, and lambda equal to 2, y will be 32 over 4, which is going to be 8, okay, which is really very simple. Now I have the value of y, the stationary points, which we already have now, is 2, 2, and 8. I will get the Hessian matrix, and getting the border Hessian matrix, the leading principal minor for the border matrix, substituting by the point, as we can see, we will find that the total cost is 96 euros is the minimum value that we will have. To answer the last part, we will remark that the envelope theory, updating the cost function to be that it's a 4 times xy plus 3x squared alpha x squared, because that change will happen just only in the costs of the top of the box. So all I have to do now is to write the objective function plus lambda times the constraint, and then I will start using the envelope matrix, the envelope theory, which means we will differentiate the function with the Lagrangian with respect to alpha, which will develop x squared. At the critical point, it's going to equal to 4. So just only an increase of 0.1 in alpha will develop 4 times 0.1 or 0.1 times 4, which is going to be 0.4. And this is going to be the effect that we will have. Unfortunately, sometimes the constraint qualification or the Lagrange multiplier method cannot be applied. In order to be able to get this exactly, we will have to do the following. We must be sure that there is a global maximum for our problem, and that the Jacobian satisfied in order to be sure that the constraint is qualified, or the constraint qualification is really valid for us. So now consider the following problem, and which is minimizing f of xy equal to y subject to negative x squared plus y cubed equal to 0. So all I have to do, step number 1, is to putting the Lagrangian function. Here is the f, and that's the constraint. Exactly like before, that's the Lagrangian function, as I told you about the time here. So getting the first order derivative, which is going to be differentiating L with respect to x, and differentiating L also with respect to y, using the constraint as you can see. Solving them together will develop that lambda equal to 0 or x equal to 0. And in these two guys, both of them will contradict the minus x squared plus y cubed equal to 0. So both of them is not going to work to satisfy the condition that we have, which means that we have a contradiction in both these two guys. We will end up having one equal to 0 in these two situations, and that's why we cannot or the Lagrange multiplier function, the Lagrange multiplier didn't succeed in analyzing this problem. For this problem in specific, remark that we can handle it using the previous methods, and we will discover that we will have a minimum point at 0, 0. Okay, now for this challenge, it's really very simple. You have x squared plus y squared, which is required to be minimized, subject to x plus 2y equal to 4. He is asking you about the critical point, and that is really very simple. All I have to do is to get the Lagrangian function, which consists of the function by itself, sub plus lambda times the constraint, and start differentiating, putting it equal to 0, solving the equations together, and you will get your solution. Thank you very much. If you have any questions, please don't hesitate to contact me. This lecture is really very important. I'm sorry that I had to be rapid at the end of our lecture, but I will go through it once more with you with the next lecture, inshallah. Thank you very much. Appreciate your time, and I hope you will go through it step by step, exactly as you saw me in this camera, just looking exactly to which step, writing everything, and trying to solve it on your own. Please also try to do some exercises from the book. Once I have a chance, I will do some for them for you. Thank you very much. Wish you the best in all times. Thank you.